Okay, so in this video I'm going to have a look at spanning sets, basis, linear dependence, linear independence. So let's just start by looking at the word span. And what we're going to do really is just look at spanning sets. So what is a span? I'll look at the definition initially, and then we'll have a look at some examples. But the definition of a spanning set is, well, if we have a set S here, and the set S consists of the vectors v1, v2, v3 and so on up to vn, then the span of S is defined as it's the set of all possible linear combinations. I'll just write down LC here. We've done a video on linear combinations previously, so you can have a look at that if you're unsure about what linear combinations are. But it's the span of the set S is the set of all possible linear combinations of S, of all of these vectors here. So in other words, you're talking about something like C1 times V1 plus C2 times V2 plus C3 times V3 and so on, all the way up to, let's say, Cn times Vn, where these C's here, we'll call them CI's, for example, are elements. They're real numbers, okay? They're real numbers. So when every single possible linear combination of these vectors here, that's what you call the span of the set of S. So for example, if I take a fairly straightforward example, let's take V1 as being, let's say 1, 0, and let's take V2 then as being 0, 1. So basically what we're talking about here is these two vectors here. So this would be 1, 1. So this is my first vector here, 1, 0. So it just goes out as far as here. And then the other one here is V2. So that goes up along here like this. So there's V2. So that's V2 there, and this is a V1 here. So the span of all of these sets then is actually R2. It's actually called a basis for R2, but I'll go through the word basis in a few minutes. Now let's just have a look at these two first. The span of V1 and V2. So let's have a look at the span of V1 and V2 is, it's all, as I said, of R2, all the two-dimensional plane, if you like. Since any vector can be expressed as a linear combination of these two here. So for example, any vector xy can be expressed as a linear combination of these two vectors here. So in other words, it would just be x times 1, 0, x times v1 plus y times v2. So you can see here what you get is x times 1, which is 1 times x, plus y times 0, and then we get x times 0, 0x, plus 1 times y. So that's just simply x, or vector xy here. So any vector xy can be expressed as a linear combination of these two here. So for example, if we take, I don't know, let's take the vector 5, 7, position vector 5, 7, that's just simply going to be 5 times v1 plus 7 times v2. So you get 5 ones 5 plus 7 times 0, so that just gives me the 5. 5 times 0 is 0, plus 7 times 1 is 7 here. Okay, so these two vectors here, their spanning set, or the span of this set V1 and V2 is actually R2, all of R2. They're actually called the basis for R2, and they're actually called the standard basis for R2. I'll define that in a few minutes anyway. But their span anyway for the moment is all the two-dimensional plane here, all of R2. Let's take another two vectors in R2. Let's take, again, I'll use V1 and V2. So let's take 2, 1 and let's take v2 here as being 1 minus 1. Now, how can I express any vector in R2 as a linear combination of these two vectors here? These two vectors actually do form a basis, or do actually span all of R2 as well. So how can I say take any vector in R2 and linearly combine these two, if you like, to form that particular vector? So what you would do actually is let's take alpha here, and we'll multiply that by 2, 1. And then we want beta, then say another constant or another real number, multiply that by v2, and we want to end up with some vector, let's say x and y here, any vector in R2. So if we do this here, let's just multiply this out. We're going to get twice alpha. I'll actually do it all in white here, I think, at this stage, just to save time. So twice alpha plus 1 times beta should give me my x here, and then 1 times alpha minus 1 times beta should give me y here. So let's just look at these two equations here. This is equation 1, let's say, and this is equation 2. Let's just add them first of all, and that will get rid of this beta here. I'll end up with 3 times alpha equals x plus y. That will give me my first equation here. Alpha is equal to 1/3 x plus y. So in other words, if I want to form some vector xy, say 5, 7 for example, 5 will be my x, 7 will be my y. I just put them into this little formula here, and that will give me this value here. I now know what I need to multiply v1 by to give me my x and y. Now I need to work out a beta formula as well, so let's just have a look at that. What will we do? We'll take equation 1 anyway, we'll write that down. So let's say 2 alpha plus 1 beta will give me my x, that's equation 1. And then I'm going to take equation 2 here, and I'm just going to multiply that by minus 2. So equation 2 by minus 2, that will give me minus 2 alpha plus 2 beta, and that should give me minus 2y. Now if I add these two, I'll get a formula for my beta. So this will just disappear here. Here I'll end up with 3 times beta. Here I'll end up with x minus 2y. So that will give me a formula for beta here then. So I'll just end up with beta here will give me, let's see, that'll be equal to 1/3 x minus 2y. So I now have a formula here for the coefficient, or what I put here in front of the v2, what I multiply v2 by. So I have a formula here for any x and y. Now I can work out what I need to multiply this v1 by and this v2 by. So any vector in R2 I can now find as a linear combination of v1 and v2. So let's do an example. Let's take any vector, let's take 5, 4 for example. Let's take 5, 4. So what would I need to multiply v1 and v2 by and add them then to give me 5, 4? So I need to find 5, 4 as a linear combination of v1 and v2. Well, let's see, it's going to be equal to, well, 5 is x and 4 is y. So my alpha is going to be 5 plus 4 here. So 5 plus 4 give me 9. 1/3 of 9 is 3. So alpha will be 3. So I need to multiply 2, 1 by 3 plus, well, let me just work it out first. 5 and 4. I want to work out beta now. So I've got 5 and 4. So 5 minus 2y. So it's going to be 5 minus 2 times 4. 2 4s are 8. 5 minus 8 is minus 3, so a third of minus 3 is actually minus 1. So beta here will be minus 1, so I need to put in a minus 1 here. So it's going to be minus 1 times my V2, so that's 1 minus 1 here. So that should work. Let's just see, does it? So I'll end up with 3 times 2, so I'll end up with 3 times 2, which is 6, minus 1 times 1, which is just minus 1. Here I'll end up with 3 times 1, which is 3, minus 1 times minus 1 is plus 1, so that will give me here 6 minus 1, which is 5, 3 plus 1, which is 4. So I do end up with 5, 4 here, and here I do end up with 5, 4. And you can do that with any vector in R2. So you can use these two vectors here to, you can do a linear combination of those two vectors to find any vector in R2. So we say that these two vectors here span R2. Now, okay, so we've looked at two different sets of two vectors. We've looked at 1, 0 and 0, 1, and we've looked at these two vectors here, 2, 1 and 1 minus 1. We found they both span R2. And they are actually both bases for R2 as well. So let me just give you a definition for a basis. So we're going to look at the word basis now. So we looked at R2. We'll just look at R2 just to keep it simple, but the same ideas apply to R3, R4 and so on. Now a basis then is, let me see, if you have a spanning set for, let's say, R2, let's say S is a spanning set. A spanning set. Let's say in R2 anyway, we'll stick with R2 just to keep it simple. Each vector in R2 can be written as a linear combination. I'll just write down LC again. Linear combination of the vectors in S, and this is the important bit, in only one way. Then S is called a basis for R2. So we had two different examples of spanning sets for R2, but if any vector in R2 can be written as a linear combination of the vectors in only one way, then S is called a basis for R2. And in fact, the first one that we looked for, certainly V1 was 1, 0, and I think V2 was 0, 1. This is called a standard basis for R2. The standard basis. Standard basis for R2. And if for R3 you would have 1, 0, 0. You would have 0, 1, 0, and you would have 0, 0, 1. This would be your standard basis for R3, and so on. Now, if you take, you can have spanning sets that are not bases. So for example, if you take, let's take again, I know I keep using the same letters here, but V1 is equal to 1, 0, and you take V2 is equal to 0, 1, and you take another vector V3 is equal to 1, 1, then these three vectors will span, they will span R2, but they don't form a basis for R2 because vectors in R2 cannot be expressed as a linear combination of these three vectors in only one way. For example, if you take the vector 2, 3, that can be expressed as a linear combination of these three vectors by doing something like this. Let's say 1 times v1 plus twice v2 plus 1 times v3. So that's one particular type of linear combination where you can form the vector 2, 3. But also 2, 3 can be formed by doing this. If you take 0 times v1 and then you take 1 times v2 and you take 2 times v3, you'll also get the vector 2, 3. So 2, 3 can be formed as a linear combination of these three vectors in more than one way, so therefore it's not a basis. These three vectors are not a basis, although they do span R2. The two vectors v1 and v2 span R2 and do form a basis, just these two vectors on their own. However, these three vectors do not form a basis. Okay, so that's let's see, spanning sets and basis. Let's just have a look at the words linear dependent, linearly independent. Okay, so let's take linear dependent. Linear dependent vectors. So if you take, let's say, the vectors 2, 3, and let's say we'll call this v1, and let's take the vector 6, 9. We'll call that v2. These are linearly dependent vectors. If you look at these on a on the two-dimensional plane here, you've got, let's say, 1, 2, 3, 4, 5, 6, and here you got 1, 2, 3, 4, 5, 6, 7, and 8, 9 here, and you got 6 here, and you got 2 here, and you got 3 here. I think they're all the numbers we need. So if you take 2, 3 here, you've got this vector here, so that would be this vector up along here. And if you take 6, 9, then you've got this point up here, so that's just going to be a continuation really, so it's just going to up along here like this, and you should end up here. That's 6, 9 up here. Now you can see that if you multiply this vector here by 3, if you triple the length of this vector here, you'll end up on this, up at this point here. Or if you multiply this vector by, let's say, -3, you'll end up somewhere down along here. So the span of this vector here, for example, both of these vectors in fact, is all along this line here, down along here, up along here, and down along here. These two vectors are said to be linearly dependent, whereas if you take our two vectors that we started with, we had 1, 0, and 0, 1 here, so we had this vector here, we had this vector here, and we had this vector here. You can see that if you multiply this vector here, let's say v1, this is v2, if you multiply this vector by 5, you'll end up out here somewhere. You won't end up here somewhere. So these two are linearly independent. They don't lie on the same line, so they're not linearly dependent. They're called linearly independent. In the three-dimensional plane, in fact, vectors that are linearly dependent will lie on the same plane, and linearly independent vectors in R3 will be on 3 different planes. So you can see it gets a little bit more complicated as you go up through the dimensions, but you can see here for our two-dimensional plane, linearly dependent vectors will be on the same line. Linearly independent vectors won't be on the same line. So to give you a formal definition then of linearly dependent vectors, so we would say that a set of vectors, so a set of vectors So let's say again v1, v2, v3 and so on up to vn is said to be linearly dependent. To be linearly dependent. Linear dependent if there exists real numbers, and we'll call these real numbers, let's say again we'll go with C1, C2, C3 and so on up to, let's say, Cn. And these are not all, this is important, not all 0. These are not all 0. So some of them can be 0, but not all of them can be 0. And we want such that C1 times V1 plus C2 times V2 plus C3 times V3 plus all the way up to Cn times Vn will be equal to 0. So in other words, if you do a linear combination of all of these vectors here using this set of real numbers here, and not all of them 0, so some of these have got to be greater than or less than 0, but when you do a linear combination of all of these, you do get the 0 vector here. And you can kind of see that if you imagine that if you do a linear combination of all the vectors on this line here, you will end up back here at 0, providing that all the numbers that you multiply each vector by are not 0. If they were all 0, it's kind of obvious. If these were all 0, then you're obviously going to get the 0 vector. But if some of them are not 0, then you should end up by, this, in other words, this line here will be equal in length to this line on this side of the origin, if you like. So when you combine them all, you should end up with just a 0 vector. But the main point to remember here is that not all of these constants here, or not all of these real numbers here, are 0. So this is what you call, this is the formal definition of linearly dependent vectors. But linearly independent vectors then is really just the opposite. It's you've got a set of vectors v1, v2, v3 and so on. It are said to be linearly independent if they're not linearly dependent. So in other words, they are linearly independent if this is true here only when all of these constants here, all of these numbers, these real numbers here, are 0. So in other words, C1, C2, C3 all up to Cn must all be 0 for this linear combination here to be 0. Whereas for linearly dependent vectors, at least one of these must not be 0, must be greater than or less than 0. Okay, so that's really it for this particular video on spans, basis, linearly dependent and independent vectors.